Hello everyone. So welcome to day 2 of VLSI interview prep. So yesterday we have completed up to XOR and XNOR gates. So now we will start universal gates with our XOR XNOR. Sorry, universal gates NAND and NOR. Without wasting any time, let us start. So today we will maximum try to complete up to sequential circuits. Maximum we will try to wind up digital electronics today. So that we can prepare EDC now. So here I am not an experienced person. I am just preparing an online so that if I am doing any mistakes, I think you could tell me anyway so that we we can prepare together. So that is the main objective here. So there is nothing like I am some experienced person or something. Now shall we start? Let us start with universal gates. So what are universal gates? So in previous class we've learned about them, right? One is NAND, another is NOR. Question is why why are we calling them universal gates? So the reason is with NAND and NOR we can design any circuit using NAND and NOR. So that is why we call them universal gates, because we can design anything. You can either design basic gates, you can design arithmetic gates and so on. So that is why we call universal gate. So when you come to NAND, it is nothing but AND plus NOT. So my output of NAND is I will do and then I will do NOT. And for NOR it is OR plus NOT. So here my output will be or A or B, and I will simply complement that one. So that is my NOR. Now so we will learn about them in detail. First we will start with NAND gate. As we have learned, NAND is nothing but AND plus NOR. So the symbol is AND. Sorry. Yeah, B. So this is the symbol of NAND. So now we will understand its truth table and so on. And there is another representation of NAND, that is inverted OR. So this will also give me NAND. Now let us go into its truth table. Let us see what I am having here. My inputs are A, B, and my output Y. So in previous video, we will have two inputs, two power and combinations possible, two power two, that is four possible combinations. Whether 0, 0, 0, 1, 1, 0, 1, 1. Now the output of NAND is A0. So when you break the line, that is will be equal to A bar plus B bar. So this is be equal. Here you will get A bar plus B bar. That is why we will say these two are equal. Now, what is NAND? So when you observe NAND gate, you will get output high when either of the input is 0. If one of the input is 0, then you will get output as 1. Now let us verify by taking A is equal to 0 and B is equal to 0. Then my output is equal to 0 into 0 bar. So 0 into 0 is 0 bar, that is 1. Similarly, A is equal to 0, B equal to 1. Then Y is equal to 0 into 1, 0 bar. So then again you will get 1. And again, if A is equal to 1, B is equal to 0. Then my Y is equal to 1 into 0, 1 and 0. So again it will give me 1. And A is equal to 1 and for B is equal to 1. My Y is 1 dot 1 is 1 and its complement is 0. We can observe here only if my both inputs are 1, then my output is becoming 0. So what I can say NAND gate, that output will be output will be 0 only when all the inputs are logic 0. So that is NAND gate. Now there is an important concept here, that is to verify the commutative and associative law. So up to this, what we have learned up to now, that are basic gates and arithmetic gates, there both commutative law and associative law both are applicable. But for NAND gate, one of them is not applicable, NAND and NOR for both of them. So we will verify that. Now let us say what is commutative law. We will verify commutative law. Commutative law is nothing but if I am interchanging A into B is equal to B into A. So that is the concept here for commutative law. Let us check that one. I'm having two inputs, NAND gate A, B. Then my output, and again I will draw another NAND gate for interchanging those inputs. So here I am having inputs A, B. No, no. Here, sorry, so I will change. So here it is A dot A and B bar, and here it is B and A bar. So these two are equal. But now let us come to associative law. Let us take three inputs for associative law. A, B, C. Here that means it is equal to A and B and C bar. In order to associate, in order to verify associative law, first I need to do and then sorry. So these two must be equal in order to verify that my NAND gate follows associative law. Here my inputs are A, B, and here I am giving C. Now let us check the, here I am get A, B bar, and here I am getting A, B bar into C whole bar. So these two are not equal. So what we can derive from this one? NAND gate obeys commutative law, but does not obey associative law. So that is the derivation that we can draw from the is commutative and associative laws. Now let us try to understand the enable and disable inputs of enable and disable inputs of AND gate. So I am having NAND. So now here I am taking A and B, and C, this is I am taking as control input. So this is my control input. Now let us verify if I am taking C is equal to 0, C is equal to 0, then my output is A, B, 0 bar. So I am having 0 bar, that will be 1. So I am having constant 1 as output. Now if I am taking C is equal to 1, then A, B, 1 bar, I am getting A, B bar. So when you understand control, enable and disable inputs. So what does my enable input means? Enable input means if my output is changing with respect to input, then that is enable input. Disable means then my output is not changing with respect to input. So that is enable and disable input. So but from observation here, even though if I am changing A and B values here, when I am keeping C is equal to 0, then there will be no change in output. I will always get 1. So that is, so this will be my disable input. So since if for C is equal to 1, we change in A and B values, my output will also change. So this will be my enable input. I hope you understood this topic. Now let us understand, as we have said, we can design any circuit using NAND and NOR, right? Now let us try to prove the NAND is an universal gate. So in order to prove that my NAND is an universal gate, what I need to do? I need to design different gates. We will design NOT, AND, OR, and XOR and XNOR using NAND. then I can prove that my NAND is an universal gate. So now let us start with the easiest of one, that is not using, we will design NOT gate using NAND. So what is my NOT output if y will is equal to a bar? So that is my NOT output, right? So I need to take one NAND gate. So I will have only one input. So I will short these two inputs and I will take as one. I am taking A, and here I am getting A into A bar, that is equal to A bar, right? So only one 2-input NAND gate is required to design MOT. Okay, now let us try to design another circuit, that is AND gate. Now we are designing AND gate using NAND. For NAND gate output is, I need to get A dot B. So my output is A dot B. What I am taking two inputs, A and B. So here my output is how much? A and B bar. Now what I need to get? I need to eliminate this NOT. So simply I need to do another NOT operation here in order to eliminate bar. So I will sort this input to the two inputs of NAND. Then my output will be Y, that will be double bar. So that will be A and B. So here what we can write, two input NAND gates are required to implement AND gate, right? Now let us design another circuit, that is OR gate. So in order to implement OR gate, we need to think out of the box. That is, you need to get A plus B, right? In order to get A plus B, what I need to do? First, I will take two NAND gates. I will sort these inputs and I will give one A and this will be my B. And now I will connect these two to another NAND gate. And this will be A bar to B bar whole bar. Right. Now my output will become A bar into A bar and B bar whole bar. If you apply De Morgan's theorem, that will be A double bar or B double bar. So that will be A plus B. Here we are requiring three 2-input NAND gates. Are required to implement OR gate. I think you understood this one. Now we will go to XOR and XNOR. XOR and XOR. Now, what is my XOR? A XOR B is equal to A and B bar plus A bar and B. So when you observe from this equation, if you directly implement by calculating and requires 2 or requires 3, not requires 1, and this is another one, and this one requires 2. Here if you are calculating like this, then you will get how much? 2, 2, 4, 7, 8, 9. So here we are requiring 9 NAND gates. So that is not possible. So that is the maximum number of NAND gates that you will do. So if you want to do minimum number of NAND gates, now let us take one NAND gate with two inputs. So this is A, this is B. First I will design the circuit and then I will try to explain. Okay, now here what we are having. So for first AND gate output is A and B bar. So same we will get to this one. And here you will get A. Here you will get A and B bar. And you will get B. So here my output is A and B bar whole bar, and here you will get B and A and B bar whole bar. Right. And when you calculate this one, and here you will get Y. So here you will get A XOR B. Now let us verify that one. I'm having A bar, sorry, A and B whole bar, NAND B, sorry, B and whole bar. Right. So these are my two inputs. So in order to, how can I calculate this one? In the calculation, how much you will get? A and AB bar plus B bar. So here you will get, if you are taking AB bar constant, A plus B. So when you try to write this one, you can write split this one, A bar plus B bar, and you will get A plus B. Then when you try to split this one, you will get A into A bar plus A bar B plus AB bar plus B bar. So this will be, this one is 0 and this one is 0. So what is the remaining? This one, that is A bar B plus A B bar, which is equal to Okay, so so I think we have verified this one. So here we are requiring how much? Uh, one, two, one, two, three, four. Four two input NAND gate are required to implement XOR gate. Now let us try to understand XNOR gate. So we know XNOR is equal to complement of XOR. So if you complement this one, you will get A XNOR B. So in order to complement this one, I need to add one extra NAND gate. So the you will total require 5 co-input NAND gates are required to implement XOR. So that is the XOR and XNOR. Now let us try to understand this one, another concept. We will to understand two-stage implementation of SOP using NAND gate. Now we will try to implement two-stage SOP equation. Now let us say I am having an SOP equation y is equal to AB plus BC plus CA. So in order to implement this one, what I need to do is I am taking 3 NAND gates. So here I am having AB, BC, CA. So here I need to add all these, right? So then I will get AB plus BC plus CA. Now if I want to only implement using NAND gate, then I need to simply make this one NAND. So we know this is equal to this one. We have studied in first slide. So here I will get AB plus BC plus CA. So this is two-stage NAND implementation or SOP using NAND. Now why let us understand why this is important. So initially we will have AND gates right here. If you are using basic gates, then you can use AND gates in place of NAND. So and here OR gate, right? So for two-stage implementation of SOP equation, so if you replace AND by NAND and OR by NAND, then you will get the same output equation. So that is why we will and use we will learn this two-stage implementation of SOP using NAND. Now let us try to solve a similar problem. Let us say I am having y is equal to AB plus EC plus D. Now here what I need to do, first I will do, first I will draw with AND gates and join them. And here I am trying to do AND OR gate. AB, BC, so this is not or D. So here I will get AB plus BC plus D. Now what I said, I need to convert this into NAND. So then here it must have D bar. And if I am doing this, and again you will get this output equation. So that is what this two-stage implementation SOP using NAND gate. 1 second. Okay, now let us go into NOR gate. Or shall we solve from important one? I'm having some questions here. Here I am given y is equal to AB plus BC. So my question is minimum number of two input NAND gates required. So here is this is my question. Now let us try to understand. So whenever you are given y is equal to like this function, first try to do its complement. Now let us find complement of this one. AB plus BC whole bar, right? So that will become AB bar and BC bar. So that will be, so now we will convert in and take the complement. In order to take the complement, I need to apply complement again, right? Then these two complements will get cancelled. All you require is this one. One AND gate for this one AND gate to both of them, and this one. Now let us try to implement. Here AB and BC are given. So here I am getting A into B bar, and here I am getting B into C bar. Now I need to implement this function, right? So y is equal to this one. Then you will get AB bar and BC bar whole bar. So we are getting y here. So this way you can simply do it. Okay, there is no need to do this one also. You can simply calculate here. You are requiring 3 NAND gates. Now let us try with another question. Y is equal to AB bar plus BC. So what I told, first find the complement of I. So Y bar will be AB bar or BC whole complement. So then that will be AB bar whole bar and BC whole bar. Then my Y will become AB bar BC bar whole bar. Right. So here what we can do, we will always get complement. So for this one, 1, and for this B, we will get 1, and for this one, we will require 1 AND gate, and this one AND gate. So we will total require 4 2 input AND gates. Required. So this is how you will do this type of questions. Now let us try to solve another question. So here I am having f of a, b, c. I am given function and here a bar plus a bar b plus a bar b c bar. Now I am asking to find minimum number of AND gates. So that is the question. Now first let us try to simplify this one and then we will try to solve. Here I am having a bar as common, right? A bar of b plus, sorry, if I'm taking a bar common, that will be 1 plus b plus b c bar. We know 1 plus anything is equal to 1, so that will be a bar of 1, that will be equal to a bar. So here in order to implement a bar, I will require only 1 2 input and okay. The other question is very much big, but if you try to simplify this one, it is very easy. Now let us try another question. Y is equal to a bar b c. So I need to implement this function. If you are getting like this, if this simplification is not possible, simply complement and you will get a bar b c whole bar. You can write as a plus with the bar, right? If you apply De Morgan's theorem. So now y is equal to what? Y is equal to, if I am eliminating these two, then I will have this one. So A bar and whole bar. So that is what I am having it. So if I am applying a we say whole bar, then that will give me how much? A bar BC. Right. Now what I need to do? Now let us calculate for this one. So here I am requiring how much for this one? This is 1, and R you require how many? For R operations we will require BC and 3. So for R you require 3, right? So 3 plus 1 4. So here we are requiring 4, and you need another one complement, another extra one. So total you require 5 2 input NAND gates. No, let us try another question. And I am having function f of a, b, c, d, that is equal to a bar, b bar, and c plus d. So let us try to solve this one. When you try to apply De Morgan's theorem to this function, then that will become a bar plus a bar whole bar c plus d. So this will be a b bar c plus a b bar d. Right. First, we will get this one. A B bar you can directly implement it. You will get if I am going to input CFP. And here I am getting A B bar. Now, what I need to do? I need to implement C. And here, okay. So this will be all bar. This will be A B bar D all. I will simply add another AND gate. Then I will get A B bar C plus A bar B D. If I am making A B bar common, and again I am getting C plus D. C plus D. So here I am requiring how many? One for this one, and one for this, and one for this. So here 1, 2, 3. So total we are requiring 4 2 input and here. Now let us go into mortgage. So when you try to learn about mortgage is nothing but R plus not. Right. The representation for NOR is R first and not. This is my NOR representation. Or I can also represent so that will be equal to variable plus sorry. Then if you do whole complement it's A plus B. This one is sorry. It will, so that is what. So these both are equal. So same concept, you know, for comparative and associative long. So first, let us verify two terms. Let us try if I can see. ABL. So what are my total possible combinations here? 0, 0, 0, 1, 1, 0, and 1. So my R will give me that is 0 plus 0. So it will give me 1. Right? 0 plus 1 bar get 0. 1 plus 0 bar you will get 1. 1 plus 1 bar and get 0. This is 0. So my output is only high if my both are low. And in all other cases it is 0. So that is OR gate. So the same concept of AND gate is applicable. We can design all the circuits using NOR as well. Now let us not waste time on designing all the circuits. But what we will do is we will now jump into one of the most important topic, that is combinational circuits. So what does combinational circuit means? So it means that output depends only on present input. It does not have any memory. No memory. It does not have feedback. And now, what are the examples of adder, full adder, mux, comparator, encoder, decoder, demux, and so on. Where you can name n number of circuits for combinational. Now let us start with how to design a combinational circuit. Now let us understand how we will design combinational. Now, first point is we need to identify inputs and output. So how many input lines and how many output lines I am having. So first we need to identify those, and then you need to write the truth table of it. Truth table between input lines and output lines. So truth table, you know what. So for this input, what is my output? So you will need to write. Then you need to write the output terms in SOP or POS, and then simplify using Boolean theorems or K-map, whichever is comfortable for you. And next, we need to implement using logic gates. So this is how you will design a combinational circuit. First, you need to identify the input lines, and then you need to draw the truth table for the circuit, and then you need to write the POS and P1 and SOP form of input and output, and then you need to simplify using Boolean theorems, and then you need to implement using logic gate. So that is how we will design a combinational circuit. So what is the first type of combinational circuit? That is nothing but half adder. So what are my input and output line? So what are my input lines? X and Y are my input lines. Sum and carry are my. So let us first draw the half adder block. So for half adder block, you will have two inputs and they will have two outputs. That is sum and carry. So now let us understand what are my inputs here. A and B are my inputs. Let us say and B and this one output is sum, and another output is carry. Now, what my does my what does it generate? So first we will write inputs A, B, sum, carry. So my sum, what is my output equation for sum? That is A XOR B, and my carry equation is A B. Now let us try to implement this one. And we will derive that formula. So for two inputs, my total four combination of possible 1 and 1. Now 0 or 0, sum will be 0, carry also will be 0. For 0 and 1, sum will be 1, carry is equal to 0. And for A or B, so it will be sum is equal to 1, carry equal to 0. For 1 and 1, my sum will be 1 and sum will be 0 and carry will be 1. Now let us write for output equation. So we need to write SOP equation, right? So for sum, what is my output equation? One second, guys.